Right now, 13 billion miles from where you're sitting, NASA is about to attempt something it has never tried before. No test run, no backup plan, no second chance if it fails. They're calling it the Big Bang. And in the next few weeks, it will decide whether a 49-year-old spacecraft keeps talking to Earth or goes silent forever. Everyone knows Voyager 1. It's the famous one, the golden record, the first human-made object to leave the solar system. But there's a second spacecraft out there, quieter, less talked about, moving through a completely different region of interstellar space in a completely different direction. And it just did something Voyager 1 physically could not do. It carried an instrument Voyager 1 lost before Ronald Reagan was even president. And what that instrument found didn't just confirm what we thought we knew about the edge of our solar system, it broke it. This is the story of Voyager 2, the twin nobody talks about, and why what happens to it in the next few weeks matters more than anything else currently happening in space. Voyager 2 launched on August 20th, 1977, 16 days before Voyager 1. The naming isn't a mistake, and it isn't a clerical error. It reflects the order the two spacecraft were expected to reach their targets. Voyager 1 was built for speed. Jupiter, then Saturn, then a sharp turn out of the solar system entirely, sacrificing everything else for a closer look at Saturn's moon Titan and a faster exit toward interstellar space. Voyager 2 took the long road, and in doing so, it became the only spacecraft in human history to visit all four giant planets: Jupiter, Saturn, Uranus, and Neptune. Every single gas and ice giant in our solar system, seen up close, in detail, by one machine. Nearly 50 years later, no other spacecraft has repeated that. None is even scheduled to try. But that longer route came at a cost: time. Voyager 1 crossed into interstellar space in August 2012. Voyager 2 didn't cross until November 5th, 2018, 6 full years later. For 6 years, Voyager 1 was already out there, alone, sending back data that was confusing scientists and forcing them to rewrite their models. But the story it was telling was incomplete, because the one instrument that could have told the full story had already died, decades earlier. Here's the detail almost nobody mentions when they talk about Voyager 1's historic crossing. Its plasma science instrument, the device built to directly measure the temperature, density, and flow of charged particles both inside the solar system and beyond it, stopped working in 1980. Not at the heliopause, not near interstellar space, before it even reached Jupiter's orbit. That means when Voyager 1 made its historic crossing into interstellar space in 2012, it did so completely blind on the single most important measurement of the entire encounter. Scientists had to reconstruct what was happening indirectly, using cosmic ray data, magnetic field readings, plasma wave signals, anything except the real direct measurement, a 32-year-old gap in the data that nobody could fill. Voyager 2's plasma instrument never died. It kept working through Jupiter, Saturn, Uranus, Neptune, and all the way out into interstellar space. And when it finally crossed the heliopause on November 5th, 2018, it delivered something no spacecraft in history had ever provided: the first direct simultaneous measurement of plasma on both sides of the boundary, separating our solar system from the galaxy beyond it. 5 papers, published together in Nature Astronomy in November 2019, laid out exactly what Voyager 2 found. And it wasn't confirmation of the theory, it was contradiction. Scientists had expected the heliopause to be a thin, sharp line, a clean boundary where the solar wind ends and interstellar space begins immediately. Instead, Voyager 2 found something completely different: a transition zone roughly 100 million miles wide, sitting just outside the boundary where interstellar material was pushing inward, tangled with the outgoing solar wind like roots pushing through rock. Then came the second surprise, and this one genuinely stumped even senior scientists. Both Voyager 1 and Voyager 2 crossed the heliopause at almost the exact same distance from the Sun, roughly 121 astronomical units and 119 astronomical units. That shouldn't have happened. One crossing occurred during a period of high solar activity, the other during a period of low activity. According to every existing model, the size of the heliosphere should expand and contract with the solar cycle. It didn't move. A senior Voyager scientist put it as plainly as possible: "We do not understand why that is." That is not a small admission from someone who has spent decades studying this data. The third finding may be the strangest of all: the heliopause leaks. Not metaphorically, literally. Particles cross the boundary constantly, in both directions. Voyager 1 detected interstellar particles pushing inward before it even crossed. Voyager 2, approaching from a completely different direction 6 years later, found solar particles leaking outward into interstellar space before it crossed too. 2 spacecraft, 2 different entry points, 6 years apart, and both found the same thing. The heliopause isn't a wall, It's closer to a coastline with the tide running in both directions constantly at the interface between two oceans. Our solar system, it turns out, was never sealed off from the galaxy around it. Before any of that happened, though, Voyager 2 had already rewritten planetary science on its way out. In January 1986, it became the only spacecraft ever to fly past Uranus, discovering 10 previously unknown moons and 2 new rings, measuring the planet's bizarre 97.77-degree axial tilt, and detecting a magnetic field so wildly offset from the planet's rotation axis that it still challenges every model of how planetary magnetic fields form. Then, in August 1989, it reached Neptune, its final planetary encounter, and one of the most productive single flybys in the history of space exploration. It discovered 6 new moons, including Proteus, a moon large enough that many scientists believe it should have been spotted from Earth decades earlier. It measured Neptune's winds moving at 2,400 kilometers per hour, the fastest winds ever recorded anywhere in the solar system, and it turned its cameras on Triton, Neptune's largest moon, catching active nitrogen geysers firing plumes of material 8 kilometers into a paper-thin atmosphere, evidence that Triton wasn't born there at all but was a captured world from the Kuiper Belt, pulled into orbit by Neptune's gravity millions of years ago. All of that from a spacecraft built with less computing power than a modern calculator designed to last 4 years and still operating today, 49 years later. Here's the part that should genuinely concern you. Both Voyagers are powered by plutonium that decays at a fixed, unstoppable rate, losing roughly 4 watts of usable power every single year. It cannot be recharged. It cannot be repaired. It can only run out. Voyager 1 already lost one of its 2 remaining science instruments in April 2026. Voyager 2 currently has slightly more power, enough to keep 3 instruments running, but that margin is shrinking by the same 4 watts every year, with no way to stop it. And once the power is truly gone, there is no backup plan. No replacement mission is anywhere near interstellar space, and none will be for decades. When these 2 machines finally go dark, humanity loses its only real-time window into the space between the stars, possibly for the rest of this century. That is exactly why NASA is about to try something it has never dared attempt before. Engineers at JPL nicknamed it the Big Bang, a complete simultaneous rewiring of every remaining power system on Voyager 2, executed all at once, with 0 room for error and no way to reverse course partway through. Why so extreme? Because every single command sent to Voyager 2 takes more than 16 hours to arrive, and 16 more hours for any response to come back. A slow, careful, step-by-step reconfiguration would leave the spacecraft stuck in dangerous in-between power states for far too long, risking automatic fault protection systems shutting things down permanently on their own. Doing everything simultaneously and skipping through that dangerous transition as fast as possible is actually the safer gamble, even though it means there is exactly 1 attempt with nobody able to intervene in real time if something goes wrong. If it works, Voyager 2 could gain a year or more of extended operational life. And if it succeeds, NASA plans to attempt the exact same procedure on Voyager 1 as early as July 2026, with hopes of even reviving the instrument that already shut down in April. If it doesn't work, there is no second attempt. Ever. 2 machines the size of small cars, powered by plutonium sealed into their generators nearly 50 years ago, are still out there in the dark between the stars, still transmitting, still measuring a region of the universe no human instrument had ever directly sampled before they arrived. And their entire future now comes down to one uninterruptible gamble, 16 hours away, with absolutely no way to take it back if it fails. The signal is still coming. Faint, stretched across 13 billion miles, carrying data from a place we currently have no other way to reach. Whether it keeps coming is something we're about to find out. If you want to know the exact moment NASA confirms whether the Big Bang worked, subscribe and turn on notifications. This is only the beginning of the story.